Yes, all day long. You know how you feel right now. If you guys see the floating controls, just ignore, hide them. You speak into the mic itself. See, it's worn out here, but this button to the right is forward, that's back.
Hello.
Okay. All right, you guys ready in the front?
Yeah. Yeah. Yes, Professor.
Okay, start anytime.
Good evening, guys. We are Team Risk Titans, and my name is Badrinath. So we today are going to give you a presentation about multi-factor industry risk analytics, which is our capstone project. And firstly, we would like to thank Professor Rollins and Dr. Rusman, owner and lead researcher of Human Capital LLC. They have provided us mentorship and guidance at each and every stage of a project. So we would like to thank them a lot for this. And firstly, I would like to introduce my team members. We have Yesu, who is the Scrum Master, Dheeraj, who is the product owner, myself, Niveda, Ankush, and Amir are the developers for this particular project. So I would like to walk you through the table of contents, which we would be explaining you today. So we would be starting with by explaining the problem statement. After that, we would be going into the domain. We would be going into the goal and the objective of our particular project as well, and we would be explaining more about the domain of the project and why this particular project is important in real world. After which we would be going more deep into our project by explaining the different phases into which we divided our project and pre-processing of our data. After that, we would be going. After that, we would be explaining about the machine learning concepts and how we integrated different machine learning concepts into a single machine learning model and why exactly we did that. And later, we would be explaining about the cascading effect as well as state transition calculation and risk calculations. And we would be going through by showcasing two demonstrations, one of which is an AWS QuickSight demonstration and another is a user interface interactive website demonstration. So I would like to introduce everyone to our problem statement. As we all know that United States regularly faces with multiple natural disasters on a year-on-year basis. The recent one being the Los Angeles wildfire, which affected the entire California state, not only the Los Angeles County. And these particular natural disasters such as floods, hurricanes, tornadoes, wildfires not only threaten the civic infrastructure but also threaten the infrastructure of many small as well as medium scale industries. And we in this particular project are targeting few key sectors like aviation, healthcare, water treatment facilities, and there is no specific tool which is being used by small and medium scale industries in order to identify and mitigate the risks which are being caused by these natural disasters. So our goal is to develop a data-driven platform using which the small and medium-scale industries can identify the risks as well as reduce the risks. And for this, and to achieve this particular goal, we are trying to use machine learning algorithms as well as performing geospatial analysis and also geographic data analysis. and integrating them with the real time the regional risk the regional data, and creating a predictive model which the small and medium scale industries can use on a regular basis. So I would like to introduce you to the domain of the problem and why exactly this problem is really important, why exactly the solution and the problem are in real time are important. So managing the impact of natural disasters like floods, wildfires, and hurricanes are really important. And we are using geospatial data and analytics to identify the regional risks. And this problem is important because natural disasters can disrupt essential services and infrastructure. Not only they don't disrupt it one at a time, but there is a cascading effect to it. So for example, if there is a disaster, so if a water treatment facility is being impacted by a natural disaster, not only that water treatment facility will be impacted, but there are a chain of industries which are dependent on that water treatment facility, which also get disrupted. So and also small and medium-sized organization lack real-time tools like this to assess disaster data, to assess the risk and work with the disaster data. And without proper planning without proper planning, recovery is really slow, and it is often most costly. I would like to hand over the mic to Niveda, who would be explaining more about our project phases.
Thanks, Badri. I'm Niveda, and I'll walk you through the project phases and the technical implementation. I'm sorry. So our project has mainly 4 phases. The phase 1, the problem framing and the data collection. We just have seen the problem framing in the earlier slides, how we frame the problem and what are our objectives. And further, we'll be discussing about the data collection, how we collected the data from different sources. And coming to phase 2, let's look at the data integration, how we have integrated different data sets and how we have pre-processed it, implicating the values. And then we also have a phase 3 data analysis and geospatial dashboard, which we have used AWS QuickSight to make the geospatial dashboard. And at last, we have a data modeling risk assessment tool, which will help us calculate the risks and using at a county level. And further, we have now let's look at the data sets. So mainly we have worked with the 3 data sets with the entire project. The first data set is the FEMA data set, which is the Federal Emergency Management Agency, which has the information about disasters and historical informations about the location, time, about the different disasters. And then next we have economic census by the industry, wherein we have information about the different kind of sectors of businesses we have dealt with. So we mainly focus on 4 sectors in this project, that is the aviation, water, and power supply. And then we have a NOAA climate data set, which is a National Oceanic, Atmospheric, and Administration data set. So from this data set, we have information about the historical weather events and the environmental trends for different regions. And now let's move on to the architecture. Firstly, we have a data collection. We just saw how we have collected the data from 3 different data sets. And then we have forwarded to the data cleaning, how we have dealt with the missing values and how we have done the multiple implications. And then we have a data integration from showing how we have integrated 3 different data sets and then made a final data set about it, and which is ready for the feature engineering. And then we have conducted the exploratory data analysis. With that, using the exploratory data analysis, we have also made a, we also have a key features from the exploratory data analysis, that is probability, hazard, consequence, or which all of them contribute to the risk of this. And then all of this is fed to the data set, which is now ready for the feature engineering. And later, once the final data set is done, we now apply the data modeling prediction, wherein we use 3 different models, such as the linear regression, XGBoost, and random forest. So using the exploratory data analysis and the results from the data modeling, we have visualizations about the geospatial dashboard using the AWS QuickSight. And yeah, we have a geospatial dashboard using the AWS QuickSight. And then we also have a risk assessment tool wherein we can assess the risk by selecting at the county level and the type of disaster we have. And now going to the data integration, the first, we have 3 different data sources, that is United Census and the FEMA and the NOAA data set. So from the first data set, the US Census, we filter out the four major business sectors, that is aviation, healthcare, and the power plant and a wastewater treatment. So from the second data set, using the first and the second FEMA data set, we have joined them using the FIPS codes and the year, and now we have made a new data set that is a disaster declaration data set with a small business count. And then using the third data set, NOAA disaster data set, which has the information about the hazard. Now we have integrated the disaster declaration data set with the small business along with the NOAA disaster data set. And now we have joined them using the FIPS codes and the hazard type. And now we have a final data set which is now ready for the feature engineering, which has the main key features as a state, county, and the business count. And now, which this lays a foundation for the feature engineering and for modeling. Now I'll let my teammate Ami take over the presentation. Sorry.
Thank you so much, Niveda, for explaining the process of merging all the data sets so clearly. So after collecting the data sets together, that is FEMA dataset, NOAA census dataset, and US dataset, so we finally created one dataset. This dataset contains all the key features which are required for our project, that is business types, property damage, and what are the incident taking place like hazards. So after then the next step is the data cleaning. So yeah, so after finalizing the dataset, first step, we removed all the incomplete and inconsistent values from our dataset. The next, our dataset contains some cryptic values like F, P, N. So we converted those cryptic values into clear labels so that we can understand easily, like F to full, N to non-operational, and P to partial. Then our dataset also contains some time-related data. So we converted the time-related data, which is in minutes and seconds, into hourly format, so that it would be easier for us to know the transitions of the businesses taking place in hourly. The next, we removed some data which is which is not useful for our project, and we also created one column in our dataset, that is previous state column. So this is because to observe the transitions taken hourly hourly, like how the businesses is changing hour to hour. And these are some of the exploratory data analysis. So in the first picture, we can see, so basically the first picture tells us which incident is been occurring the most. So we can see that hurricanes is been occurring the most, almost 72,000 declarations, followed by severe storms, which is almost half of the hurricanes. So we can say that hurricanes is the most making the most disruption in our data set. Next picture tells us which state is being affecting the most. So basically Louisiana and Texas are leading the table with almost 22,000 and 20,000, followed by the other states. And this is a heat map, so which tells us the incident counts happening, changing through year to year from 2013 to 2025. So we can see that hurricanes, if you see the hurricanes, so in the year 2017 and 2018, we can see significant spike, which is in dark blue color. It means it is most active in those seasons. And we can see severe storms is almost light blue in all the seasons. That means it occurs, it's recurrently occurring. So like for observing the transitions of the businesses, so we have involved the new term Markov chains and cascading effects. So I will hand over it to my teammate Yesu. He will be explaining.
Thank you, Amir, for giving excellent data insights. So now we can do our feature engineering and model training with our target variable, but wait, we don't have a target variable at this point. That is our risk score. So for calculating that, we are lacking with one term, that is state transition probability, which we call as hazard. But so how we calculated, so we considered two different methods here, simple methods. There's a cascading effect. We all know cascading effect is the effect. So whenever, which refers to a system when one step in the system, failure of one step in the system leads to failure of all the steps in the system. For example, whenever a war starts at some place in the world, so which leads to, if that country is engaging in exporting oil, all these things, then oil supply first disrupts, and after that the countries which are importing the oil, so they need to pay more. So that's why so inflation increases in those countries. So obviously stock market drops, and which leads to the investors who want to, who put their assets in risky assets like stock market, want to move their assets to safest assets like gold and silver. So the decay is happening in the whole chain of events. So whenever initial event what starts leads to happening failure of all other events like this. So we consider the decay from cascading effect for calculating our state transition probability. And after that, the Markov chain. Markov chain is a mathematical model. So the current state depends on only the previous state. So for example, now the state is full means what is the previous state? So how the previous state that, so the current state depends on like that. So here like this, we ran our simulation for calculating our state transition probability. So for each state, county, business type, and for each hour, we ran a simulation. So here we took the present state, what is the present state probability. So which we calculated from the previous state probability as well as the decay rate. Decay rate is how likely a system degrades over the time. So decay rate resembles the cascading effect here, and the previous state depicts the Markov chain model. So now we have all our three terms to calculate, find our target variable. That is the probability, hazard, and damage. Probability is nothing but the likelihood of an event happening in a place, likelihood of hazard happening in a place, and hazard is the state transition probability, how we calculated by considering cascading effect or Markov chain in the last slide. And the damage property is the how much damage happened in terms of $1 million, which we took from NOA dataset. By multiplying all these three terms, we finally got our risk score, final risk score, which is a target variable. Like this, we got 6 types of risk score. So we consider for business like 3 different states, like full, non-operational, partial operational. So how the transition happening in each state, like that we calculated our risk. So this is not enough to directly give a target variable to model training. We need some more intermediate steps. So those intermediate steps will be explained by Dheeraj.
Thank you, Yesu. So as Yesu mentioned, in order to get targeted risk scores, we need to perform some intermediate steps. They are power transformation and min-max scaling. As for power transformation, in our case, we calculated risk formula. After that, the data distribution shows right skewed, which means all values near to zeros. In order to change the distribution, we performed power transformations. And as for min-max scaling, since our project includes linear regression, which is based on Euclidean distance, we performed min-max scaling to normalize the data. So after these 2 steps, we have achieved the final targeted risk scores. After that, we have developed an AWS QuickSight dashboard. How we did it? First, we have uploaded the dataset into S3 bucket, and we imported the dataset to QuickSight via S3 bucket, and then we enable the location-based analytics using county level. After that, we delivered an interactive dashboard using 6 median average risk scores, and here is our demo. So this is our dashboard, and the scale shows 0 to 0.82. 0.82 is the highest average risk score according to our data. So this is one of the county in New Hampshire showing 0.61 risk. And then next example takes Los Angeles County showing 0.58 risk score, comparatively lower than the other one. And the final one is Elko County showing 0.43 risk score, which is comparatively lower than the other two. Until now, we have finished our phase 3 of our project. Now Ankush will be explaining the next phase.
Thanks. Thanks, Dheeraj, for explaining about the QuickSight dashboard. Now let's go to the final phase where we have modeling and the web application tool. So as you can see over here, the model we have used over here is an ensemble model, which is a combination of 3 different models. The first one being linear regression, random forest, and XGBoost. So the individual R2 scores that we have achieved for these 3 models were 0.55 R2 score for linear regression, 0.70 for random forest, and 0.76 for XGBoost. So once we were done with this combination of 3 ensemble models, now, so basically, why did we choose an ensemble model and why not just use a single model? So there are 3 main reasons for us to be choosing an ensemble model. The first being diversity. So we could see that there were a few data points where the data was kind of giving accurate results on linear regression, but was not performing well when it came to random forest or XGBoost. So for us, it was very important to include this diversity, and so that our model gets robust and the accuracy increases. And coming to the second point, we have the error correction. So as you can see that one of the base model that we have used over here is XGBoost. We made sure that whenever we have stacked up models one after the other, we make sure that one model tries to correct the error of the previous model. So this was one of the aspects that we wanted to have, and that's the reason. Finally, coming to the the final point is better generalization. As you know that as we when we try to use a single model, we see that there is a problem of the bias and variance. But when we try to use multiple models, we are able to balance the bias and variance. And in a way, this helps to generalize our data and gives us better results. So now, once we were done with the ensemble model, we still had issues when talking about the R2 score. We thought that we should still be able to improve our model. So let me just give you an example how hyperparameter tuning came into the picture over here. So in the beginning, we divided the historical data into 2 parts, 70% given to the training data, 30% to the validation data. And then once all the 3 base models that were made into an ensemble model and were given for training, this trained model was used to validate the data of the 30% and give results. So the evaluation metrics over here that we have used is the R2 score and the MSE scores. Once we got these scores and our end goal was to improve these scores, we did an hyperparameter tuning for 2 models, that is XGBoost and random forest. So the 3 parameters that we have chosen over here for the hyperparameter tuning is the number of estimators, the max depth, and the learning rate. So as you can see, we have chosen few random values and used grid search CV to accomplish this process. So for the number of estimators, as you can see, 100, 150, 200, 250. So these are the number of trees that we have used. Then coming to the max depth, 5, 10, 15, 20, 25, and learning rate from 0.02 to 0.1. Finally, after performing the hyperparameter tuning, we could achieve an R2 score of 0.85, which was pretty good compared to the before model where we had achieved about a 0.82 as the R2 score. So now, as we are coming to an end for our presentation, I would just like to give a quick summary of what we have done up until now. So initially, we began with collecting data from the presidentially declared datasets website, U.S. Census Bureau, and then since the data had a few issues regarding state and county levels, we had to merge an extra dataset which had the FIPS state codes, so that we don't have discrepancies when we try to connect the counties and the states for a particular disaster. And then talking about the consequence term over here, since for the risk formula calculation, as you can see, we needed the three terms. So one of the term consequence had to come from NOA dataset. So we had merged the NOA dataset. And then once we got the hazard term by the risk matrix, we merged it with the final dataset and calculated the risk score. So this final data set was then uploaded into an S3 bucket, and then with the help of Amazon QuickSight service, we were able to showcase a geospatial dashboard which would tell the different risk scores of different state and counties, as my teammate Dheeraj had explained earlier. Next, since we also had to make a prediction tool which could show that what is the exact risk score for a particular business in a particular state and county, we performed the power transformation and min-max scaling, gave the data for model training, and then finally created the website for the risk prediction. So now we'll just give you a quick demo of our risk prediction tool. So on the left side, as you can see, we have different options. So let's just take a state of California over here and select the county Santa Clara. So this is the time frame over here. That is, once a disaster hits a particular county, you can just select how many hours has been passed after the disaster has struck. So let's just take 24 hours. And we have 4 business categories over here, as we explained before. So let's just take hospitals and healthcare. And we have 10 disasters. So for California, let's select fire. And then we have the current state of the business. So this explains either it's partial, full operational, or non-operational. What is the state of the business? So here we have first the risk bar scores, which tell what is the likelihood that the full operational state will go to non-operational. Next, we have the top 5 counties for California fire. This is just a visualization, talking about Los Angeles County being the highest. Then we have a bar chart which explains about the top 5 disasters that happen in California. Fire being the highest with 7,307 events, followed by floods, severe storms, and earthquakes. Next, we also had more insights on risk trends. This could be explaining about the R-axis that we have on the X-axis, and so that we get quicker insights on how the risk probability is changing over the period of 5 days. So here we have considered 0 to 120 hours over here. And as you can see that the risk score is increasing for partial to non-operational state from 0 to 120 hours. And similarly, at the same time, the probability that the business will go from partial to full operational is decreasing. So this is one pretty good insight for any business owner to just have a look at it and understand that in the next 5 days, what is going to happen and how can they take precautions regarding this disaster that has struck. So now, as we have come to the end, I would talk about the future scope for our project. So given the time frame that we had, we made sure that we created a good foundational base for the future data enthusiasts to take forward this project and try to add a few more enhancements to our web application tool and the QuickSight dashboard, so that it would really be very helpful for the small businesses. So there were a few things that we as a team identified which could be improved, and so that it could be a very useful for the businesses and the government. So the first point being business impact estimation model. Now, as you can see, our risk prediction tool was able to provide the risk scores, but was not clear on how much monetary loss could a disaster have. Could a disaster be impacting on a particular business? Second is incorporate additional sectors. Now, as you can see, we have discussed about only 4 business sectors. We could add up two more additional sectors such as telecommunication and education, and then finally a mobile system alert system which would just give an SMS as soon as there is a disaster struck, and tell us about the different risk scores that are happening. So with this, I would like to conclude our showcase presentation for the capstone project, and we are open for questions.
There are no questions online, but Dr. Rasmussen, if you're online, if you'd like to unmute yourself, if you'd like to say a few words.
Sure, that was a great presentation. I appreciate all the work the teams have done. These are some pretty awesome projects, especially with the variety of subjects that the teams covered. Congratulations.
I actually had a couple of questions I'd like to ask, if you don't mind. So which data set provided the incident information?
So for the incidents, we had the FEMA data set, which would be talking about the federal emergency data set, talking about US presidentially declared data sets. The
Okay.
FEMA.
So that was your criteria, was presidentially declared
Yeah.
disasters.
Yes. Presidentially declared data.
And that came from FEMA?
FEMA, yes.
Okay, and what did the NOAA data set provide you?
So NOAA dataset provided us about one of the term called consequence, which tells us about the damage that has taken place due to the disaster in the particular state and county.
Okay, and so this is all historical data. It's just, is it predictive in any way, or just representative of what they could potentially expect should a similar disaster occur in that area?
So we had 2 demos. One was about the AWS QuickSight, which showcased the historical data and what are the risk scores for a particular state and county depending upon the disaster that has happened. And the another web application tool which would predict the risk if you provide a particular business and a particular disaster that takes place. So there were 2 aspects to it.
So you mentioned that you will be combining the 3 data sets, right? Like
Yes.
on that, so there is like in the first data set, it has like something like 300K values over there, and it is like some other has like little more values. But when you're saying like you combine all the 3 data set and you got like roughly around 20K or like something like that. So doesn't that loss of data bother about the risk factors?
So you were saying that after combining, why has the number of rows reduced?
Yeah,
Is that
I'm just
your
asking
question?
like the number of rows is reduced. So doesn't that let's say if you have like 20 rows and you just by combining you just have only 10 rows in your actual working time. So rest remaining 10 does not affect your risk factors.
So we had data for like for FEMA, but for NOA dataset, as I've explained, that there's a consequence term. So we didn't have the matching dataset according to what FEMA had. So we had to just take the few rows which were matching and use it, because if we would impute, there could be a bias in the model, and that's the reason why we see a reduce in the number of rows.
I'd like to add just 2 comments. one comment. Great job. Great presentation. Loved the Ben Franklin quote.
Thank you.
That was excellent. Just curious, you considered other data sources other than the three that you selected? I mean, those are really good sources, but had you given thought to other data sources?
So mostly our project was focusing on US presidentially declared data sets. So we had considered FEMA for the reason. There were a few different websites as well which would talk about disasters, but those disasters didn't have a greater impact on the business sectors that we have discussed. So for us to have a proper model and a realistic view, we had to take FEMA as a trustful source.
Okay. So I like the ensemble approach that you took. The R2 scores looked really good, but I think the model could be extended elsewhere outside the U.S. That's where I was going with, because I think it's, from a general perspective, you could, depending on the data source, you're going to have to change how you were doing your merging and things like that and filtering. But I think overall the process is a good process. So congratulations.
Thank you.
All right. Thank you, team. Before everybody leaves, I want to thank everybody who participated online. I'm going to end the webinar for now.
I'd like to give a round of applause for everybody here. It was just really great today. And I'd like to thank Professor Schmidt, who did a fantastic job putting this all together. And we did 20 today. This is the most we've ever done in one setting. So we appreciate you for being here from 7 to 7. I know it was a long time. Professor Schmidt and I and Dr. Gang, we have to do it all.